60% of families who buy Lego robotics kits never get past the first 3 projects. The reason isn't lack of interest or ability, it's infrastructure failure. Software that won't install, workspaces too cramped to test anything, expansion packs bought too early that just create clutter, and surprise costs that kill momentum 6 months in. I'm Rajiv Patel, and I've spent 15 years in systems integration watching the same planning mistakes tank corporate deployments and home learning labs alike.
You're listening to the STEM Lab podcast. Quick note before we dive in. Everything you're about to hear, the research, the data, the script itself, comes from real authors with real expertise. This voice, though, is AI-generated. We wanted to be upfront about that. If you've listened before, thank you for being here. Seriously, if you're new to the show, welcome aboard. We publish new episodes every Monday, Wednesday, and Friday, covering practical STEM education strategies that work in actual homes without unlimited budgets or advanced engineering degrees. Now, here's what we've got for you today. A Lego STEM setup delivers real value only when you address 4 infrastructure categories before you ever buy hardware: software compatibility across operating systems, physical space with proper power distribution, expansion planning tied to actual learning milestones, and the full picture of consumable and subscription costs over a 2 to 3 year skill-building cycle. This checklist eliminates the setup delays and compatibility failures that derail most initial Lego robotics deployments in home labs. I've deployed this exact framework for my own children and for corporate training environments. The same principles apply in both contexts. You're building a progressive learning environment, not assembling toys. Now, let's talk about software and platform requirements. Your Lego STEM setup fails immediately if software dependencies block your child from writing code. Lego platforms span 3 distinct programming paradigms with 0 interoperability, so you need to verify these requirements before unboxing hardware. Lego Education Spike Prime requires iPad OS 14 or later, Chrome OS 103 or later, Windows 10 Build 16 299 or later, Mac OS 10.14 or later, or Android 7.0 or later. The app is a 400 megabyte download with mandatory cloud account registration. Offline mode exists but disables lesson library access and progress tracking, so plan accordingly if your child works in environments with unreliable connectivity. The platform uses Scratch-based block coding and Python, specifically a MicroPython variant, making it the only Lego system supporting text-based language transition within the same hardware ecosystem. Lego Mindstorms EV3 shipped with desktop software that Lego officially sunset in January 2024. You now rely on third-party environments like the EV3 Classroom app for iOS, Android, and Chrome OS, or open-source Python libraries like ev3.dev. If you're running Windows 11, expect compatibility issues with the original desktop IDE. The EV3 hardware remains functional, but software support has shifted entirely to community-maintained forks. That's acceptable for advanced learners comfortable with documentation gaps, but problematic for beginners expecting guided curricula. Lego Boost Creative Toolbox uses a proprietary tablet-only app for iOS and Android with no desktop support. The app requires 1.5 gigabytes of storage and works exclusively via Bluetooth 4.0 LE. USB connectivity doesn't exist. This creates a hard ceiling at visual block programming with no migration path to text-based languages. It's acceptable for ages 7 to 9 building foundational logic skills, but you'll replace the entire platform when transitioning to Python. WeDo 2.0 uses Scratch-like block coding via a dedicated app or Scratch 3.0 extension. Schools receive perpetual licenses. Home users pay yearly subscriptions for lesson content, running $35 to $40 per year as of 2026. The hardware connects via Bluetooth LE or a USB dongle that's included. Critically, WeDo bricks are not compatible with Mindstorms or Spike Prime systems. They use different motor and sensor protocols and cannot interoperate despite using standard LEGO Technic mounting holes. Once your child masters block-based interfaces, industry-standard tools become relevant. Spike Prime and Mindstorms hubs support MicroPython via Visual Studio Code extensions, enabling professional IDE workflows with Git version control, debugging breakpoints, and library management. This represents the actual career preparatory phase, the transition from educational sandbox to tooling used in embedded systems engineering. Budget 20 to 30 hours for this migration, even with strong Python fundamentals. LEGO education platforms require account creation with parental consent mechanisms. Student data flows through LEGO servers for progress tracking and curriculum delivery. The privacy policy complies with COPPA and GDPR, but you're accepting cloud dependency for core functionality. Offline operation degrades to basic programming without lesson scaffolding or achievement tracking. Moving on to physical space and power infrastructure. LEGO STEM platforms demand more real estate than marketing images suggest. A 36 by 24-inch workspace represents the minimum viable footprint for building, programming, and testing cycles without constant teardown. I measured these requirements across 18 months of continuous use. Your child needs a flat, stable surface, maintaining at least 30 inches of clearance in front for robot movement testing. Spike Prime's hub uses USB-C charging at 5 volts and 2 amps minimum. Mindstorms EV3 requires a barrel jack AC adapter or 6 AA batteries. Bluetooth-dependent platforms like Boost and WeDo eliminate tether constraints, but introduce battery replacement costs. Budget $8 to $12 per month for AA rechargeables. NIMH with 2000 mAh or higher capacity with a 4-bay charger. Mount a power strip with surge protection within 24 inches of the build area. USB charging blocks should deliver 2.4 amps per port to avoid slow charge delays exceeding 3 hours.
LEGO elements accumulate rapidly. Spike Prime ships with 523 pieces. Expanding to competition-level builds easily reaches 1,500 parts or more across motors, sensors, structural beams, connectors, and wheels. Use transparent drawer organizers with 12 or more compartments. Commercial organizers like Acromills work well. Label drawers by component type. Motors, sensors, beams by length, connectors by type. This system reduces build prep time by 40 to 60% compared to dumping everything in a single bin. Store sensors in anti-static bags if your environment runs below 30% humidity. I've seen 3 capacitive touch sensors fail from electrostatic discharge in dry winter conditions. Spike Prime's color sensor and future vision-equipped sets require consistent ambient lighting at 500 lux or more. Inconsistent lighting creates sensor calibration drift, particularly with color detection algorithms. Add a swing-arm LED desk lamp with 5,000 Kelvin color temperature and 800 lumens or higher to eliminate shadows during testing. This isn't optional for computer vision projects. Insufficient lighting triggers 70% or more of sensor malfunction support tickets I've reviewed. Line following, maze navigation, and autonomous mapping projects demand 6 by 6 feet minimum floor area. You need smooth, flat surfaces. Carpets with pile height above a 1/4 inch interfere with optical odometry and create traction inconsistencies. I recommend laminate flooring, hardwood, or low-pile commercial carpet tiles. Mark a permanent testing grid with painter's tape in 1-foot squares to standardize distance measurements and repeatability testing. Electronics generate minimal heat, but human comfort matters during 90-minute programming sessions. Maintain 65 to 75 degrees Fahrenheit ambient temperature. Lithium batteries in hubs degrade faster above 80 degrees storage temperatures. Avoid direct sunlight on hub screens. The Spike Prime hub's LCD washes out completely above 10,000 lux incident light.
If multiple children share the lab, allocate separate storage bins and separate programming devices to avoid workflow conflicts. LEGO Education software supports multiple student profiles, but Bluetooth pairing to hubs creates device switching friction. Expect 2 to 3 minutes to disconnect and repair when switching users. A second tablet or laptop eliminates this delay for households with siblings on parallel learning paths. Let's talk about expansion packs and curriculum progression. LEGO platforms use a base set plus expansion pack model that mirrors enterprise licensing. You buy entry-level hardware, then purchase additional components as skill milestones require new capabilities. This section quantifies the actual expansion path costs.
The base Spike Prime set includes 3 motors and 4 sensors. The LEGO Education Spike Prime expansion set adds 603 pieces, expanding structural possibilities and enabling multi-motor drivetrain designs like 4-wheel drive or dual-arm manipulators. At approximately $115, this represents a 50% cost increase over the base set. Justification threshold: your child has completed at least 15 base set projects and explicitly encounters mechanical design constraints requiring additional motors or beams. Premature expansion creates parts bin clutter without skill advancement. First LEGO League Challenge divisions for ages 9 to 16 publish annual game rules requiring specific mechanical capabilities, typically 2 motors for drivetrain, 1 for manipulator, plus color, ultrasonic, and gyro sensors. The base Spike Prime set covers 80% of typical season requirements. Budget $80 to $150 for additional specialty pieces like large wheels, specific gear ratios, or extended beams. Teams competing at state or national levels commonly invest $300 to $400 beyond the base set across a 4-year progression. This converts LEGO from learning toy to industry-standard robotics training platform. FLL alumni demonstrate 3 times higher acceptance rates in engineering programs according to internal FIRST research data. Spike Prime motors and sensors use powered-up protocol. Mindstorms EV3 uses legacy protocol. They cannot interoperate. WeDo components use yet another protocol. If you own multiple LEGO platforms, treat them as completely separate ecosystems requiring dedicated expansion purchases. The only shared components are passive Technic structural elements like beams, connectors, and gears. This fragmentation represents LEGO's most significant design flaw. You cannot build a unified parts library across product lines. Brands like High Technic, Mind Sensors, and Dexter Industries manufacture EV3-compatible sensors, thermal, compass, acceleration, unavailable in LEGO's catalog. Spike Prime's newer ecosystem has limited third-party support as of 2026. For advanced projects requiring specialized sensors, the aging EV3 platform paradoxically offers greater expandability despite discontinued official software support. This matters primarily for high school students designing competition robots or science fair projects with non-standard sensing requirements. LEGO Education sells teacher-facing curriculum guides for $150 to $250 per year per platform with 40 or more hours of structured lessons. Home users access truncated free content via the programming apps, but comprehensive project scaffolding requires paid subscriptions. Alternatives exist. Platforms like Tufts University's LEGO engineering curriculum offer free resources covering mechanical principles, programming logic, and project design. Budget 8 to 12 hours reviewing free curricula before purchasing commercial lesson packs. Most families find free resources sufficient through intermediate skill levels. Motors fail, though it's rare, typically after 500 or more operating hours. Sensors drift out of calibration. Structural beams crack under repeated stress. LEGO maintains a replacement parts program at approximately 60 to 80% of retail pricing for individual components. Budget $40 to $60 per year for consumable replacements in active labs running 6 hours or more weekly. Battery costs add another $30 to $50 per year for rechargeable AA systems or USB power banks with 10,000 mAh minimum capacity for full-day competition use. Now let's get into subscription services and ongoing costs. The LEGO STEM setup includes hidden recurring costs that compound over multi-year learning paths.
I've tracked these expenses across 2 children over 36 months. Here's the actual financial model. Basic programming apps like Spike Prime and EV3 Classroom are free, but curriculum content requires annual licenses. Home Edition Spike Prime curriculum costs approximately $35 to $40 per year and includes lesson guides, assessment rubrics, and video tutorials. Schools receive volume discounts. Individual families pay retail. The content quality justifies the cost if your child lacks external instruction, no robotics class at school, but free alternatives from university STEM outreach programs often match 70 to 80% of the value. LEGO platforms store programs locally on tablets and computers, but cloud backup requires third-party services like Google Drive, iCloud, or Dropbox. Budget 5 to 10 gigabytes for a year's worth of projects, photos, and documentation. That's negligible cost if you already maintain cloud subscriptions, but worth accounting for in isolation. More critical, version-controlled discipline. Teach Git basics once your child transitions to Python. Industry employers expect repository management competency, and robotics projects provide authentic use cases for branching, merging, and rollback workflows. First LEGO League team registration runs $225 to $275 per season, which runs August through April. Add $50 to $100 for event participation fees, team shirts, and travel to regional tournaments. This represents the highest ROI investment in the LEGO ecosystem. Competition experience teaches deadline management, collaborative debugging, and presentation skills absent from solo home lab work. I've directly observed hiring managers prioritize FLL experience equivalent to 1 to 2 years of general robotics coursework. LEGO hardware lifespan exceeds 5 to 7 years with proper storage, but software platform migrations force upgrades. The EV3 to Spike Prime transition exemplifies this. Families purchased EV3 sets from 2013 through 2020, then faced software sunset, forcing migration to Spike Prime at a $400 or higher replacement cost. Plan for one major platform replacement every 4 to 5 years if maintaining cutting-edge software compatibility. Alternatively, embrace legacy platforms for foundational skills. EV3 remains fully functional for teaching core concepts. Then migrate to non-LEGO platforms like Vex or Arduino for advanced work. High-quality third-party books and courses range from $15 to $60 each. Titles like the LEGO Mindstorms EV3 Idea Book or LEGO Technic Tinkerer's Advanced Projects provide project inspiration beyond official curricula. Budget $80 to $120 per year for 2 to 3 books, plus occasional online course access on platforms like Udemy or Coursera for robotics courses using LEGO as project platforms. These resources extend platform value and prevent skill plateaus between major curriculum milestones. Science fair presentations, portfolio documentation, and competition engineering notebooks require poster boards, color printing, and binding materials. Budget $30 to $50 per year if your child pursues external validation opportunities like competitions, science fairs, or portfolio building for high school engineering programs. This cost category often surprises families focused solely on hardware expenses, but documentation skills directly transfer to professional engineering workflows, where communication determines project approval more often than technical execution. For families evaluating LEGO against alternative platforms, compare total 3-year cost of ownership across similar capability milestones. LEGO's higher upfront cost, $300 to $500 for competitive-level setups versus $80 to $200 for Arduino-based alternatives, balances against lower time to productivity. LEGO's integrated ecosystem reduces troubleshooting overhead by 60 to 70% compared to breadboard and wire platforms. That time savings matters for families prioritizing completion of projects over learning low-level debugging. Here's your final check before you go. Validate these items before committing to your LEGO STEM setup.
For software compatibility, verify your operating system version meets minimum requirements for your chosen LEGO platform. Confirm Bluetooth 4.0 LE support on your programming device. Test the app download and installation, keeping in mind that 400 megabyte to 1.5 gigabyte storage requirement. Create your LEGO Education account and verify the parental consent workflow. Identify which features work offline versus which require cloud connectivity for your environment. For physical infrastructure, allocate a 36 by 24-inch minimum dedicated build surface. Install a power strip with surge protection within 24 inches of the workspace. Acquire transparent component storage with 12 or more compartments. Verify you have 6 by 6 feet of floor space for navigation projects on a smooth, flat surface. Add task lighting at 800 lumens or higher with 5000 Kelvin temperature. For expansion planning, map skill milestones to expansion set purchases, not simultaneous with the base set. Verify competition requirements if you're pursuing first LEGO League participation. Identify third-party sensor needs for specialized projects. Locate free curriculum resources before purchasing commercial lesson packs. Budget $40 to $60 per year for replacement parts and $30 to $50 per year for battery consumables. For subscription and recurring costs, calculate your 3-year total cost, including curriculum subscriptions, at $35 to $40 per year. Plan your competition budget, if applicable, $225 to $275 per season plus travel. Allocate funds for supplementary learning resources at $80 to $120 per year for books and courses. Schedule a platform upgrade evaluation at the 4-year mark. Establish a cloud backup workflow for programming projects. Let's address some frequently asked questions. Can I use LEGO Spike Prime sensors with Mindstorms EV3 motors or vice versa? No. Spike Prime uses the powered-up protocol, while Mindstorms EV3 uses legacy LEGO Mindstorms protocols. They are electrically and logically incompatible. Only passive Technic structural elements like beams, gears, and axles can be shared between platforms. This fragmentation requires maintaining separate inventories if you own multiple LEGO robotics systems, and it prevents consolidating expansion investments across product lines. If you're building a long-term learning path, commit to one platform through intermediate skill levels before migrating to Arduino or Raspberry Pi systems that offer genuine cross-compatibility. How much physical space does a functional LEGO STEM lab actually require for a middle school student? A middle school student working on competition-level projects requires a minimum 36 by 24-inch build surface plus 6 by 6 feet of adjacent floor space for autonomous navigation testing. That's approximately 45 to 50 square feet total when accounting for chair clearance and component storage. This exceeds typical desk setups and often necessitates commandeering a corner of a bedroom or dedicating a section of a basement or garage workspace. Families without this footprint face constant tear-down rebuild cycles that reduce project completion rates by 50 to 60% based on patterns I've observed across home labs. Do LEGO education platforms require ongoing subscription payments, or are they one-time purchases? The core programming software, like the Spike Prime app and EV3 Classroom, is free with permanent access, but comprehensive curriculum content requires annual subscriptions ranging from $35 to $40 per year for home users. You can operate indefinitely without subscriptions using free resources from university outreach programs and community-contributed lesson plans, though you lose structured scaffolding and assessment tools that justify the cost for families without external instruction sources. Cloud storage and competition participation add separate recurring expenses. Budget $300 to $400 per year total if pursuing competitive robotics pathways, or $50 to $80 per year for casual skill building without formal curricula. Here are my final thoughts.
A properly configured LEGO STEM setup functions as a multi-year technical skill platform, not a weekend project. The checklist above prevents the most common deployment failures: software incompatibilities discovered after unboxing, insufficient workspace forcing constant teardown, premature expansion purchases creating parts bin chaos, and unanticipated recurring costs derailing long-term commitment. I've watched both successful and failed implementations across dozens of home labs. The distinguishing factor isn't budget, it's infrastructure planning completed before purchasing hardware. Families treating LEGO robotics as isolated products fail within 6 to 9 months. Those implementing systematic learning environments with proper software, space, expansion planning, and cost management produce children who transition successfully to Arduino robotics platforms, Raspberry Pi projects, and eventually industry-standard CAD and embedded systems workflows.
The framework documented here scales from initial SPI prime deployment through competitive robotics and into professional engineering pipelines. Your child's first line-following program today connects directly to motion control algorithms in manufacturing automation, autonomous vehicles, and aerospace systems. That progression only succeeds when you build the infrastructure supporting continuous skill development rather than isolated entertainment.
That wraps up this episode of the STEM Lab podcast. Thanks for listening. New episodes drop every Monday, Wednesday, and Friday, so you've always got something fresh waiting. If you found this episode valuable, I'd really appreciate it if you'd leave a 5-star rating and write a quick review. It sounds like a small thing, but it's genuinely how other parents and educators find the show when they're searching for this kind of content. And if you haven't already, hit subscribe or follow so you get notified the second a new episode goes live. I'll see you next time.